Hello friends, I am Pankaj Jain, Assistant Professor in Physics, Engineering College, Bikaner. In this video lecture, we are going to discuss about Maxwell's equations. Let us move on topic. Maxwell's first equation is basically Gauss law in electrostatics. All we know that according to Gauss law in electrostatics, the net outward flux from a closed surface is equal to 1 upon epsilon naught multiple of total charge in the volume enclosed by the surface. Okay. Enclosed by the surface. Therefore, all we know that surface integration of electric field may be written as total charge divided by epsilon naught. This is Gauss law in electrostatics. Now, what we are going to do, we are converting surface integration into volume integration, and it can be done using Gauss divergence theorem. Let us move on next page. Here what I have done, I have converted surface integration into volume integration, and it can be done using divergence. uh, uh, Surface integration of electric field is equivalent to volume integration of divergence of electric field. Okay, this is equation number 2. And also what we are going to do, we are converting total charge in charge density. Therefore, summation q may be written as volume integration of charge density, that is rho. Okay. Using these two equations, equation number 2 and 3, in equation 1, what we get? We get divergence of E dot dV, integration of divergence of E dot dV is equivalent to 1 upon epsilon naught integration of rho dV. If we transfer this quantity, all this quantity in left hand side, what we get? Integration of divergence E minus rho upon epsilon naught dV is equivalent to 0. Okay. Now dV cannot be 0, therefore divergence of E should equivalent to rho upon epsilon naught. This is differential form of Maxwell's first equation. Differential form of Maxwell first equation, and equation number 4, and equation number 4, this equation this equation is integral form of Maxwell first equation, and this equation is differential form of Maxwell's first equation. Let us move on next page. We are going to study Maxwell's second equation in this page. Maxwell's second equation. Maxwell's second equation is basically Gauss law in magnetism. Okay. All we know that single magnetic pole does not exist. Single north pole or single south pole does not exist in nature. South pole and north pole always exist in pair, and strength of these poles also equal. Let us see this diagram. uh, in this diagram I have shown a magnet. Outside the magnet, magnetic field lines are south to from north to south pole, and inside the magnet, magnetic field lines will be from south to north pole. Therefore, magnetic field lines are always closed curve. Magnetic field lines are always closed curve. If we take a closed surface in magnetic field, then total magnetic field lines entering in this surface will equivalent to total magnetic field lines exiting from this surface. Therefore, magnetic flux from a closed surface will always equivalent to 0. That is, integration for closed surface of magnetic field will always equivalent to 0. This equation is integral form of Maxwell's second equation. Integral form of Maxwell's second equation. Now what we are going to do, we are converting surface integration into volume integration. It can be done using Gauss divergence theorem. Okay. Here I have converted surface integration and volume integration. Therefore, what we have, divergence of P dot dV is equivalent to 0. dV cannot be 0, therefore divergence of P will always equivalent to 0. And this equation is known as differential form of Maxwell's second equation. Okay, let us move on. Third topic, that is Maxwell's third equation. Maxwell's third equation is basically Faraday's law of electromagnetic induction. All we know that if magnetic flux crossing a closed curve, a closed loop changes, then EMF will induce in the loop, and induced EMF is equal to rate of change of flux. Induced EMF is equivalent to rate of change of magnetic flux, that is E can be written as minus d phi by dt. Minus sign was given by Lenz. We are not going to consider Lenz law here. This is Faraday's law itself contain Lenz law. Okay. Now EMF can be written in terms of electric field, and how we can write it? EMF can be written as line integration along a closed curve of electric field, that is line integration of electric field E. Okay. And magnetic flux can be written as surface integration of magnetic field. Phi m is magnetic flux, and it can be written as surface integration of magnetic field. Okay. If we use equation 2 and equation 3 in equation 1, what we get? We get line integration along closed curve of electric field is equivalent to minus d upon dt of surface integration of magnetic field. This equation is known as integral form of Maxwell's third equation. This equation is known as integral form of Maxwell's third equation. And what I have done here, I have used Stokes curl theorem to convert line integration into surface integration, and it can be done by taking curl of electric field. Here I have E dot dl, here I have curl of E dot ds. In this way I have converted surface line integration into volume integration. Okay. If this quantity, if this quantity is transferred into left hand side, what we get? Let us move on next page again. We get integration of curl E plus del B upon del T dot ds is equivalent to 0. Okay. Here ds cannot be 0, as well as dot product between them cannot be 0 always. Therefore, for the validity of this equation, we should write curl of E is equivalent to minus del B upon del T. And this is differential form of Maxwell's third equation. Okay. Now let us move on. Maxwell's fourth equation. What is this? Maxwell's fourth equation is basically Amperes law in magnetism. According to Amperes law in magnetism, line integration of magnetic field along a closed curve is equivalent to mu naught multiple of total current crossing the surface and closing by closed curve. And mathematically, the Amperes law may written as in equation 1. Okay. Now, if we change line integration into surface integration using curl theorem, what we get? We get line integration of B along a closed curve is equivalent to surface integration of curl of B. Okay, let us move on next page. Also, total current is written in the terms of current density J. All we know that summation I is equivalent to integration J dot ds. Therefore, current is written in the form of current density. Using equation 2 and 3 in equation 1, what we get? We get integration of curl B dot ds is equivalent to mu naught integration of J dot ds. Okay. If I transfer this quantity into left hand side, what we get? Integration of curl B minus mu naught J dot ds is equivalent to 0. ds cannot be 0 and dot product cannot be 0 always. Therefore, curl B should be 0. Curl B should be mu naught into J. Okay. Let us check the validity of this equation. And to check the validity of this equation, what we are going to do, we are taking divergence of this equation both sides. What we have, divergence of curl B is equivalent to mu naught divergence of J. All we know that divergence of curl of any vector quantity is always 0. Therefore, divergence of curl B will 0 always, because divergence of curl of any vector quantity is always 0. Using this in equation, in above equation, this equation, what we get? We get divergence of J is equivalent to 0. Let us move on next page. And according to equation of continuity, we have divergence of J plus del rho upon del T is equivalent to 0. If divergence of J equivalent to 0, then del rho upon del T will equivalent to 0. That is, rho is equivalent to constant. Then what I want to say? I want to say equation number 3. Equation number 3 will valid only if rho will be constant. Okay. Equation number 4, will valid only if charge density is constant with respect to time. If charge density is not changing with time in space, then equation 4 is valid. If charge density is changing, then equation 4 should be corrected. And the correction was given by Maxwell. He wrote equation 4 in this manner. He wrote curl of B is equivalent to mu naught JC plus JD. Here I should have used vector sign. Curl of B is equivalent to mu naught JC plus JD. Here JC is what? It is conduction current density, which was also given by Ampere. And the term added in JC is JD, and it is what? It is displacement current density. The concept of displacement current and displacement current density was given by Maxwell. Okay. This is corrected form or improved form of Amperes law. Let us move on next page. And here we have discussed already displacement current density Z is equivalent to epsilon naught dE upon dt, where E is what? It is electric field. Okay, E is electric field. And putting this in above equation, what we get? Curl of B is equivalent to mu naught JC plus mu naught epsilon naught dE upon dt. This is called differential form of Maxwell's fourth equation. In this way, we have studies all Maxwell's equations, and fourth equation is basically modified form of Amperes law, and it was given by modification was done by Maxwell. Thank you.
We know that displays. ये क्या कर रहा है ग्रीन से? ग्रीन ये किससे कर रहा है? ये ग्रीन किससे कर रहा है पापा? पापा ग्रीन किससे कर रहा है? ये ग्रीन किससे कर रहा है? पापा ग्रीन किससे कर रहा है?
बता दूंगा मैं तेरे को।
पापा आपको इरेजर क्यों चाहिए था?
Hello friends, in this video lecture, dear students,